Welcome to this skill builder on an introduction to hypothesis testing in statistics. Hypothesis testing occurs in all sorts of different subjects that use experimental research, especially in the sciences such as biology, chemistry, physics, medicine and more, as well as the social sciences such as psychology or sociology. And these are just some of the main steps that we follow when we test hypotheses. So what happens is, in step 1, an experimenter identifies a problem that needs to be solved or a question that needs to be answered, and they define their hypothesis, which is a tentative answer to the research question. We'll cover that in more detail in a minute. Then in step 2, to be able to find out what the answer is, they design an experiment that will test their hypotheses. And this involves manipulating one variable and measuring the outcome of another. In step 3, they go out and collect the data that they need. In step 4, once they have their data, they will need to report the descriptive statistics or characteristics of the data. And this includes measures of central tendency and variability. In step 5, the data is analysed using a statistical test. And finally, in step 6, they interpret and present the results. The reason why we test hypotheses is so that we can make informed, evidence-based decisions. It allows us to draw inferences about the characteristics of a larger population based on a smaller sample that we've taken from it. And this process helps to contribute to new knowledge, allows us to build on existing knowledge, and advances understanding in various fields of study. To help you understand what I mean by making inferences about the characteristics of a population, I'll talk you through a simple example. Let's say that we want to know the average height of all of the people in the UK. The parameter we're interested in is mean height, but it would be impractical or even impossible to measure the height of every person in the country. So we take a sample of individuals from the population and measure the height of every person in the sample. This allows us to calculate the mean height of our sample, which represents our parameter of interest. And that representation of our parameter of interest is what inferential statistics is all about. Because we don't know for sure, but we get as close as possible to knowing what that true parameter is by making an inference based on what we've calculated from our own sample of data. Or in other words, the sample mean is an estimate of the population mean. And this process of estimating parameters is called statistical inference. We make an educated guess about the population parameters based on our own sample. In hypothesis testing, an experimenter makes a claim that a certain manipulation will lead to a change in that parameter of interest. So this usually involves collecting data from a control and an experimental condition. The control condition doesn't undergo any kind of manipulation. The experimental condition does undergo some kind of manipulation. And the experimenter forms a hypothesis, which is a tentative answer to the research question. Then to test the hypothesis, they manipulate the independent variable and measure the dependent variable. Some key concepts of hypothesis testing that you need to know are the experimental or alternative hypothesis, which is our belief about the effect that our experimental manipulation will have. It states that there is a relationship or difference between groups. The null hypothesis is the opposite. It states that there is no relationship or difference between groups. And you'll also need to have an understanding of significance level, or alpha, which is the probability of rejecting the null hypothesis when it is true. And we'll get to that in just a minute. To give you an example, an experimenter starts with a research question, which in this case is, does beetroot consumption improve endurance performance? Based on that question, they need to define their experimental and null hypothesis. So in this example, the experimental hypothesis is runners in the experimental condition will run at a faster velocity than those in the control condition. The null hypothesis is that there will be no difference in running velocity between experimental and control conditions. They manipulate their independent variable and measure the dependent variable. So in this experiment, in this example, the independent variable is baked beetroot consumption, and the dependent variable, the variable that they're measuring, is running velocity. So half of the participants might be put in an experimental condition where they eat beetroot before running, and the other half would be put in a control condition or a placebo condition where they just eat cranberry relish before running. Based on our hypothesis, we'd expect that running velocity would be faster in the experimental condition versus the control condition. But to find out, we'd need to use a statistical test to compare running velocity between the two groups. The results of a stats test will give us a test statistic and a corresponding p-value. So firstly, the test statistic indicates how closely the data matches the null hypothesis. Secondly, the p-value shows the probability of obtaining the result if the null hypothesis is true. If the p-value is low, there's a low probability that the null hypothesis is true. So that means that the experimental hypothesis is more likely to be true. If the p-value is high, there's a high probability that the null hypothesis is true. So that means that the experimental hypothesis is less likely to be true. To determine whether to accept or reject the experimental hypothesis, we look at the significance level. So we usually work to a predetermined significance level called alpha, and this is usually set at 0.05 or 5%, which means that there's a 5% chance of making a type 1 error. And a type 1 error is also often referred to as a false positive. And that is when we reject the null hypothesis when it's actually true. The key thing to remember is that if the p-value is less than 0.05, the results are significant. They support the experimental hypothesis. If the p-value is higher than 0.05, the results are not significant. They do not support the experimental hypothesis. So it's all three of these things on this slide, test statistic, p-value and significance level, which allow us to determine statistical significance. Our research question, hypothesis and the type of data that we have will allow us to choose which type of statistical test is most appropriate. There are three main varieties of stats tests to choose from. Tests for correlation measure the strength and direction of an association or relationship between variables, for example, time spent revising and exam marks. A regression can be used to model the relationship between variables and predict or estimate the effect of one or more independent variables on the dependent variable. For example, we could predict how a change in temperature will change a household's electricity consumption. Tests for comparison are used to look for differences between two or more groups or conditions. For example, we might want to know if a new type of drug will reduce blood pressure in patients with hypertension. We might give one group of patients the new drug and the other a placebo, and then the test for comparison could tell us whether there is a significant difference in average blood pressure between the two groups. Other stats skill builders cover more specific examples of some of these types of tests. These include Pearson correlation, linear regression, the t-test for comparison, and more. For guidance on the broader range of stats tests, please go to the Skills for Academic Success website at kent.ac.uk/SAS, where you can view more of our numeracy and statistics videos. You can also book a one-to-one appointment with one of the SAS team.